Thanks, Queenie. Happy to be here in the closing talk. And this is what I am going to talk about. It's some things we have been thinking and trying to see what are the trade-offs we have to do to build the best proof aggregation virtual machine. And this is like the overview of my presentation. The idea is we will talk a little bit about the verification problem, then why we want the ZKVM, and then a little bit on the design decision trade-offs and, of course, conclusions. So the idea was that we wanted to have verifiable applications, and the easiest way to do this was by having each party re-execute the computation and reach an agreement that is consensus. The problem with that is every node has to do the same amount of work, and so the situation does not scale. Okay? But with succinct proofs, what we can do is, in fact, delegate the proving to just one node, and the rest have to verify, and the amount of work they have to do is much smaller than the prover. In fact, it's much smaller than having to re-execute the computation. Okay, so in this way we could solve the scalability issues by offloading execution to some of the nodes. But the problem with this and what we are facing right now is that verification on top of Ethereum is like super expensive because first, we cannot exceed 30 million gas per block on proof verification, which more or less translates to you cannot verify more than 10 proofs per second. And so if we want to make this something massive, of course, with 10 proofs per second, we are not going very far. We cannot parallelize, we cannot use hardware acceleration, and besides, we have to code for a metric which is gas consumption and not speed. And also the cost depends on the existence of precompile, so that limits the amount of choices that we have. And so what happens then is that here there is like an idea of the costs and everything that we have in Ethereum for proof verification, and so we need a strategy to reduce this amount of money we're spending every day on verification. Rollups can spend like several $1 million per year just on proof verification, not counting other expenses. And so one way we can reduce this cost is by bundling several proofs into a single one using the idea of proof recursion. That is to say, proving that I verified several proofs. Okay? So next to why do we need zero-knowledge virtual machines? Well, first, because they simplify the development of verifiable applications, because we can code right now ordinary code and then execute it on top of the VM, and the VM handles all the problems related to using ZK. Okay, so we abstract all the difficulty related to ZK from the developers as much as we do with other programs that precisely take out all the gory details. Of course, circuits can be more performant, but the problem is that they are harder to develop. They are perhaps more bug-prone, and it's the same as if you coded in assembly language. And something nice about the VM is that if it can prove, for example, RISC-V, then if a new proof system appears, we can execute that and perform proof recursion rather easily, while if we were using circuits, it would take more time. So here we have a first like trade-off, which is VMs or circuits. Of course, circuits could be more performant, but on the other hand, they are way harder to develop and to deploy. Okay? So here are some of the design decisions we are faced when trying to build our ZKVM. First is the proof system to use. So here we face things such as, are we going to use Starks? Are we going to use Circle Starks? Are we going to use elliptic curves, okay? Right now, I think we are converging on the idea that Starks are way better because of some of the advantages that they offer. Of course, for some protocols, it makes sense to use elliptic curves because they want other properties. Then, even though we may agree on the proof system, there are like some other choices which are related, for example, to what finite field are we going to use, or in the case of elliptic curve, what elliptic curves are we going to use? Are we going to use just one, a cycle of curves to have like easier recursion? In the case of finite fields, we can say, okay, baby bear, but we could also use Mersenne 31, which from the point of view of hardware is much nicer. Then, of course, we have other things we have to think on the VM, whether we are going to make it modular or monolithic, that is to say, whether we are going to accept different coprocessors and we are going to split the execution trace among several tables, or whether we are going to have just one general VM. Of course, then we have the idea of the instruction set architecture. Okay, are we going to prove RISC-V? Are we going to have our own ISA? Okay, of course, building your or having your own ISA offers you some advantages because you can tailor it to be more easily provable, but on the other hand, you have to develop the compiler, and of course, developers may be unfamiliar with what you are doing, whereas if you use RISC-V, of course, you benefit from the larger pool of developers that are present. Then another point has to do with how you're going to represent the relevant variables. For example, in some cases, you're using in elliptic curves very large fields, and so in that case, any 32-bit variable can be represented by one of these elements. Of course, then the problem is you have a huge overhead. In some cases, they prefer working with byte-type variables. Sometimes they work like working over U32, so that gives some options. Another thing that we have to think about is whether we will have like two VMs, because, for example, if we want to run a very large program, the execution trace can be huge, or even our field cannot handle that. So the idea is we could split or put some checkpoints in the program and develop some kind of continuations and sharding. And the problem with that is that then we have to link all these pieces, and that is done usually by proof recursion, okay? And so do we want a separate circuit for proof recursion? That is to say, kind of having like two separate VMs. Then we have also an idea on the levels of recursion. We can benefit, for example, from having continuations and recursion, or whether we can have some type of folding. Of course, folding first was developed for elliptic curve proof systems. Now there are like some studies that show that it should be possible to do it with Starks, and the question is how performant are they, but should they be really good? That would change things a lot. Then, of course, we have different types of lookup arguments, and also how we are going to break those variables. I am going to talk a little bit later on that. Then we have also to think, okay, about the memory. Maybe the memory is just write once or read only, or we can modify the memory. Of course, then we have to be very careful on how we constrain everything to ensure that no malicious behavior is possible. And then, of course, we have to choose if it's modular, which coprocessors we are going to have, how we are going to handle the different operations and all that. So among the trade-offs, of course, you have the issue of larger proofs, for example. So, for example, some VMs, what they do is they introduce a final step where they wrap it in Graph 16 proof, for example, or a Plonk proof. And so that reduces the amount of data they have to send on chain. In some cases, of course, you would trade smaller proofs for longer proving time, okay? And you have to see whether it is acceptable. In some cases, the VM has more components, but it may take more time to develop. Another point is related to the lookup arguments. We not only have like, okay, which lookup argument we are going to use. For example, we could use logup or logup with GKR. And it's not straightforward to see which one is the best lookup for applications. In fact, there were like some benchmarks and everything showing that, for example, GKR with logup is not necessarily more performant than ordinary logup. And then, for example, sometimes they break things into bytes, and then they do some byte checkups, or lookups. But maybe we could do instead of that lookups using U16, for example. And that would reduce, for example, the number of variables we have to, for example, rain check at the expense of checking over a larger table. So this is another point where we have to see. And then, of course, we have like some general ideas related to the complexity of the code base, the VM, and of course, the generality and the kind of problems we can prove. And well, we are really excited about all the kind of things we will be able to build with this. For example, if we can aggregate proofs really fast, then of course these could open the door, for example, to having real-time proving or something like that. And this may become real sooner than we expect. So it was nice to explore some of these design decisions and everything. So thanks a lot for your attention.
Thanks, Tiago. Really enjoyed this thought process running through. Yeah. Any questions? Final one? Yes, final one.
Thank you. Can you tell me more about like the lookup argument parts, please?
Okay, so for example, in some cases you want to do U32 arithmetic, for example. You want to do integer arithmetic, for example, with a U32, with two U32. So one way you could do it is you split it into its component bytes. So it's 4 bytes. And so you have to, when you constrain the operation to be able to prove it, okay, you have to ensure that each byte is in fact a byte, okay? It has values in the allowed range. Then, of course, you also have to consider the carries from when you add 2 bytes, it may overflow. So, and in that case, you have like 3 carries, you have to check for 1 overflow, and you have to do several rain checks. At least you have to do 8 rain checks, 1 for each of the bytes. But maybe if you do it instead using U16, the amount of carries is reduced to 1, and you have to do only 4 lookups, but it's over a larger table. Of course, if you were using something like the older lookup arguments, which are dependent on table size, it may not be advantageous because you would have to look over a larger table. But in this, where you use multiplicities and many of the multiplicities are 0 because the values are not used, maybe it makes sense to use lookups or over larger tables because, in fact, your lookup argument is kind of independent of the table size.
Yeah, because at first I thought it's like, lookup tables at FHE fields or kind of like a similar concept or something. Yeah, thank you for the...
Hi, you compared using custom ISA versus something like RISC-V standardized. So I wonder, for example, in RISC-V, there's allocation in the instruction set for custom instructions. So maybe have you considered like defining a ZK specific instruction extension for RISC-V to have kind of the best of both worlds.
Yeah, no, some projects are precisely doing that, trying to extend and have like delegation to a specialized coprocessor or something to handle that. But yeah, that's an option. The other is just building your own ISA, okay? And in that case, maybe you have to deal with some of the difficulties of the compiler, but of course then that may pay off, really. I think that in the case of Lita, they were going like that way. And we have to see, but I don't know. I liked a lot the approach of, for example, the Cairo VM of having to develop something, and that was great, especially at the beginning where we didn't know whether this bet on having zkVMs would pay off. Of course, right now that we see all the development that we have and everything, it seems like it was the right call, but you never know. So it was great.
Yeah, I mean, personally, I feel like the amount of infrastructure that you would have to build for a custom ISA specific for ZK is immense, because it's not just the compiler, you also need debugging tools and simulators and all these things. But yeah, thanks.
Hi, I have a question that's really simple. Like, which part do you feel is the most sticky part for design zkVM? Like, when you pick that thing, then you have to go everything with it. Like, is it proof system or the basis or the ISA?
Yeah, no, I think that the problem is they all interact together, so it's hard to separate. Of course, I think that proof system impacts a lot. That's why, for example, I think that Start-based VMs have taken a lead. But of course, there are like some interesting projects using elliptic curves. The Nexus VM, for example, is very interesting, and the construction is really elegant. So we still have to see. Many of these are still under development, and we have to see the cool optimizations they can add, and maybe they can also, in some cases, leverage all the power of hardware acceleration. So we still have to see, and I don't know, there have been like many new developments and research that show that we can get even better.